Welcome everyone. In this video I'm going to show you my new project, and this will be a little bit more exciting project as my other projects, because this will involve a lot of high power stuff and possibly some spectacular things as well. And this will be the first video in this kind of series, because I'm planning to create more and more videos with this kind of equipment, but now I will just guide you through this system. And then in the upcoming videos, you will see more and more experiments, hopefully in a nice way. So I think you can guess by the parts that I show you here on the display that this is an induction melting equipment, and this will be used to hopefully melt small amounts of metals. I don't know how high I can go with the melting point, so what kind of metals and what amount of metals I can melt, but I will test it. That's why I built this equipment. And most of the things here that you can see is off-the-shelf parts, except a few parts which I had to 3D print for myself, because I wanted to fix different parts to this frame, and therefore I needed some custom-made parts. So for example, here is a thermometer, and then this thermometer is sitting in a panel, as you can see, and this panel is 3D printed, but in the background you can see a water pump with a reservoir, and that is also sitting on a 3D printed piece of plastic. And then I will show you some other parts when I show you the other side of this device. Those parts are also attached to a custom designed and 3D printed plastic part. And this brings us to the sponsor of this video, PCBWay. PCBWay is a service provider specialized on PCB manufacturing and PCB assembly, but they also have other nice services such as CNC machining and 3D printing, both in metal and plastic. If you want to order PCBs from them, you just go to their website, PCBWay.com. You select PCB Instant Quote, and after clicking the Quick Order PCB, you can upload your Gerber file, and after customizing your board based on your needs, you can save it into your cart and send the order after a review. And if you are in a similar situation than I was during this project, and you need custom-made 3D printed parts, you can still go to their website and select the CNC machining and 3D printing option, and then on the corresponding page you can upload your CAD file and then customize your material and finally submit the order. So I hope that you like PCBWay's services and you will use them. And now let's start from the front panel of this device. So I already introduced you this part here, and this is a simple thermometer which is attached to a thermocouple, or the thermocouple is attached to this panel to be more precise, and the thermocouple will measure the temperature of the water in that reservoir there. So that is just to check how hot is the water which is cooling the rest of the things. And here in the front you can see a 10-turn induction coil. I haven't measured the diameter of it, but I can really easily check that because I have a ruler just next to me. So roughly 65 millimeters, the inner diameter. And then this induction coil is driven by a 2500 watt ZVS driver. So that's why you see those two colossal fans, because they are blowing the cold air through the heat sinks, which cool down the MOSFETs which are switching the power here. And then on the right side here you can see this panel, which is a DC power meter. So this will measure the power which goes from the high performance power supply, this guy here, to the ZVS driver, and we can measure the current and the power and the voltage in the line and so on and so on. And then we have two switches, and one switch here on the left side that will turn on the water pump, the fans, and it will also allow us to switch on the solid state relay, which is switching the power between this power supply here and the ZVS driver here. So without this switch being turned on, we cannot do anything with this switch. This switch is only for switching the solid state relay on and off and nothing else. But this is connected to the circuit in a way that it requires the 12-volt power supply to be turned on already. So without cooling, we are not able to run the ZVS driver and the induction coil. And here you can see the front panel of a telecommunication power supply. It's approximately 3 kilowatts or 3000 watts. That's its peak power. And it can provide 48 volts DC and 62 amperes. So it is just perfect for this device, because this requires roughly 48 volts. I don't exactly remember the figures, and it can take up to 50 amps. So then this power supply is perfectly matched to this 2.5 kilowatts ZVS driver. So now I will tilt the camera a little bit and we will check the insides of this device, because that is even more exciting than the front panel. So let's see that. So I put the camera on a stand and we have a top view of everything, and I will explain you everything starting from the mains power input. So I have this cable. This is a C19 cable and it is accepted by a C20 type of socket. I will show you a picture of this socket and then you will see how this is attached to it. So the mains power comes in here, and then I have the ground, the live and the neutral wires. They go directly in this 3 kilowatt power supply, and then parallel to that I attached 3 wires to this other power supply, which is a 12 volt 5 amps power supply. And then it's not visible from this side, but I also attached the ground to this metal frame. So that should make the metal frame and everything which is metal and in contact with these things safe. So then let's start with the DC, the high power DC. So you can see that we have a thick wire, and this is a 16 square millimeter wire. It is for batteries, but I think this is enough for this application as well. So the positive wire goes to the positive side of this 80 amps solid state relay, and then when it is switched, then it leaves the solid state relay and it goes to the positive terminal of this ZVS driver, and then it does its job, and then it leaves through the black wire, also a battery cable 16 square millimeters, and goes into this black thing here, which is a shunt resistor, and this is for the power meter, which is here, this black box here. So then the current passes through this shunt resistor. It will create a voltage drop there, which is measured by this box here. And then obviously we can calculate from that voltage and the known resistor what is the power. And then the black wire goes back to the negative terminal of the DC power supply. So this is the high power part. And then I go back to the solid state relay, because we can go to 2 parts from here. One is we have 2 wires here, which is just the switching wires for the solid state relay. And they are directly connected to this switch here, which is the switch number 2, let's call it like that. And one pole of that is going to the positive side of this extension PCB here, because this is the, let's say, the terminal series of terminals for the 12 volt power supply. So I can connect everything more easily here. And then the positive wire goes in to the switch, the negative comes out, or the other wire comes out and goes to the positive switching part of the solid state relay, and then the negative side just goes back to the ground, so nothing fancy there. And then the other part which is attached to this solid state relay is a 4x4 centimeter water cooling block. It's at the bottom, and you can see the two pipes or tubes coming out here. So how it goes is that the water starts here from the pump, and then it goes directly into this water cooling block. It cools down the solid state relay, and the slightly warm water goes here, and then this is an 8 to 6 millimeter diameter adapter. So then a smaller diameter tube goes there to the induction coil, and then that same tube comes back. Here is that other wire, or other tube, sorry. It goes under this connection here. It goes back to 8 millimeters, and then it goes here, and it's not really visible, but I put a T junction there, and one side here is connected to a valve. So if I want, I can drain the water without messing up the connections and everything. And then after this T junction, the water goes into the radiator at the bottom. Then it goes, circles around the radiator, and then it leaves at the top, and then it goes back to the pump. And why I made like this, like pumping in the water at the bottom fitting and having the water leave at the top fitting, is because of the bubbles. So I can get rid of the bubbles very easily, so there will be no air inside the radiator if I do it like this, because then the bubbles go with the flow. It's more easier to get rid of them. So that the water cooling part is explained. So then we have this other power supply, this smaller one. It's a 12 volt 5 amps DC power supply, and what I did is that I created a custom tiny prototype board with a lot of terminals on it. One side is the positive side, other side is the negative side. And first of all, the 12 volt which comes out goes to the switch number 1. So I can switch this extension part on and off. And then when I turn it on, that powers on these two fans on the ZVS driver. It powers on these 3 fans on the radiator. It powers on this pump. And then we have the thermometer here at this corner. So that is also powered on. And finally, since the switch number 2 is also connected to this, now it allows us to switch on the solid state relay. So then that's how it works. And then what I have here is then I have a thermocouple, and then I just open this hole here with this nut, which is screwed into this top of the reservoir, and then I just put this thermocouple in, so I can measure the temperature of the water. So that's a good indication how the cooling is going on. So basically this is all regarding the, let's say, composition of this structure. Yeah, one more thing is that the frame, I just used these regular 20 by 20 aluminum profiles. I ordered it from a company and they cut it to size for me. So the length and the width of this frame is 42 centimeters. And then the height, so this column here is 25 centimeters. And they are attached together with some corner pieces. And then we have this plastic here, which is a polycarbonate plastic sheet, this corrugated sheet. And it is used for gardening or making small roofs and so on and so on. So you can buy it in a regular hardware store. I also bought it in the local hardware store. So yeah, this is regarding the other things which I should talk about. So now we have one task left only, is that we need to make this thing run. So I already prepared another thermometer just to check the water thermometer if it is measured properly. And then I made a, let's say, safety handle. So I have this screwdriver and I will try to heat this up. but then I hold the screwdriver with this grip, and then I also hold the grip here. First of all, if I accidentally touch the coil, I will not get shocked, hopefully. And this also adds an additional distance because this thing can get quite hot. Additionally, I have a infrared thermometer. I will try to measure the surface of the copper, but usually these things don't work very well with the shiny metal surfaces, so we will see. And you can see it on the left side here. I have a power meter, so I will also measure the consumption of this device. So now I rearrange the camera again, and I will show you the experiment. And it will be noisy because this big power supply has a tiny but very powerful fan in the front. So we will see or hear how my voice will be during this noise. I hope you will still hear most of the things. So I have rearranged the experimental setup, and we are looking at the front panel right now. I put the power meter also there to a visible place, so hopefully we will see the power consumption, but at least I will always see it when I do the experiment. So then I will be able to read it easily and tell it to you while I'm recording this video. So now I will start the device by switching on the main switch on the back, and that will start this power supply, which will be really noisy, so hopefully you will still hear me. So I switched it on. You see the LED. And now probably you can hear the annoying noise. And here you can see that we have 48 volts on the main line, which is perfect. And there is no power flowing because this is off. And this is also off. And this 4 watt hour is just, let's say, the standby consumption. And I can see that that power meter is telling us 17 watts of power consumption. So now I turn on the cooling part. And now we see the water temperature here, which is jumping for some reason, but this is what we have. And now the power consumption there jumped up to 32 watts. So now basically there is one thing left. I just start the induction coil, and we will see what happens. So now I see 5 amps of consumption, but there is no metal here, so that's kind of the standby power. And then here you see the other power to 244 watts. But now I see that this device shows 290 watts, and now I should use this screw here, or screwdriver rod, and put it in the coil. So that will kind of complete that, let's call it transformer. And once that circuit is complete, that will increase the power here. You will see it. Now you can see it's already brown, but that's just surface oxidation. But you could see that the power consumption went up. And now it's glowing already. As you can see. And you can see the different temperatures there because you have different colors and they correspond to different oxides or different thickness of the oxide layer, to be precise. And since we have different thickness there, it will create different color. So that's why you see a bit gold color and then purple and then blue. So this is the water temperature, and as you can see, it's pretty much room temperature also there. And also at the back I can read 300-ish, 30-ish temperatures. So that's pretty much fine. So I turn this off. And then I turn this off. And then I turn this noisy thing off as well. So now this shut up. So as I could see it on this wattage meter or power meter, the power consumption was not too high, 500-600 watts maximum. So that's, yeah, not too much, I would say. It was still something. And as you could see, with that 500 watts, I was able to heat up this until glowing. And basically that was my intention for this experiment, just to see if this thing works reliably, and it seems to work reliably. If I touch the solid state relay, that's still cold. So you can see that there is still potential in this system, because I can draw 5 times more power out of this thing. So that will be done in the next experiment, because now I don't have crucibles or anything. And one thing that I have to emphasize here is that this was a very unsuccessful experiment when I did this. And why? Because the diameters are not matched. So I should not expect, and I was not expecting, I knew this already, that if I have this diameter, 65 millimeters of inner diameter, and if I put something in which is like 1 centimeter in diameter, they are not, let's say, coupled well. And due to this issue, because of the poor coupling, not too much power will be transferred from the, let's say, magnetic field into the material. So then I would expect that if I have a thicker piece put in here, then I would have much better heating effect as well. So that's why you put a very thick crucible in this, and you heat that thing up, because that matches the inner diameter of this thing. So before finishing this video, I just want to show you some teaser, because of course I don't want to use this coil all the time, and I made my own coil for a very funny experiment, and that will be this coil here. And you can see that this is wound in a very funny way. As you can see, the diameter of this is progressive, in a sense that it's higher diameter here, or larger diameter here, and smaller here. But also what you should see is that we have this loop here. And this coil is very interesting, because from the top, when I start from the top, I go clockwise with the thread, and then I come out with this loop, I go back, but then I continue the winding counterclockwise with the bottom parts. So what this will do is, if I'm not wrong, the bottom part of this coil will try to act against the gravity, and it will try to push up the material, and the top part will try to push it down. So there will be a net force acting on the specimen put inside the center of this coil, and the magnetic field plus the gravity will somewhere find a balance, and the sample will simply float here. And this is not any let's say sophisticated levitation stuff or fake stuff. This is real. So what you do is that when you create this AC magnetic field with the coil, that induces eddy currents inside the material. And if you have currents, you have magnetic field. So you generate a magnetic field inside or within the material as well. So there will be one magnetic field which is introduced to the material, and the magnetic field is also present inside the material due to the eddy currents. So then you have two magnetic fields acting against each other. So then what you have here is that where the winding flips from clockwise to counterclockwise, there should be a zone where the material inside is both pushed upwards and pulled downwards, and that net force will keep the magnetic or magnetized material there. So that's a very funny experiment. And I have already kind of made the fittings, but to re-plumb everything and do the wiring again with this new coil would require some time because I have to drain the system. So I will do that in an upcoming video, but hopefully that will be very soon, and I hope you will be excited to check this, because if I can do this at a small scale, that will lead us to some very funny stuff. So this is all what I wanted to show you. I wanted to give some teaser of this project, and I hope that you will like this project. I put quite a lot of work and resources in this, so I expect nice results from this melting equipment. So hopefully it will work reasonably. So I put some extra images of this device, of the different parts of the device, and the schematics of the plumbing, the hosing, and also the wiring. So please visit my website, link is down in the description. Also don't forget to visit PCBWay.com, because they have amazing services and they have amazing products as well. So please check them out, and if you want to make these custom-made 3D printed parts, or you want to make your own PCB, feel free to use their services. So I hope that you learned something. I hope you found this video interesting, and see you in the next video.